So guys, today we are going to be talking about crystals and how they interact with linear algebra, how linear algebra can explain some of crystals, how you can use in linear algebra, the application of linear algebra to find angles within crystals and as well as dimensions. But first we need to start off with what is a crystal? Well, crystals are just coordinate polyhedra arranged in a specific orientation. But, well, what is a polyhedra? Polyhedras are just simply the coordinates for points on a polyhedron, like a tetrahedron or an octahedron. But, I mean, that doesn't really give you a great example of what a crystal is. Crystals are really a crystal structure, which equals, you get your crystal lattice and your unit cell times your unit cell. And really, the unit cell is a subset of your crystal lattice because the unit cell is the smallest symmetrical formation of a molecule. And the crystal lattice is the infinite arrangement of unit cells with transitional symmetry when related to each other. So really, the unit cell, you can kind of think of the unit cell as a basis because that's what everything else in the crystal is formed off of. And then your span for what you do in the crystal is just how much of the substance you have. If I have 3 water molecules, then obviously it's not going to go on for infinite. Infinite is just if you had infinite material, it would go on for infinite arrangements. And if you look at more dimension, you can look at crystals in 3D, in 2D, and 1D actually, but 1D is just like, it's just a row. It's just a regular crystal lattice like this. We're about to go into a 1 that you might not expect to be a crystal formation in 2D, and then we'll look at some 3D examples in a little bit. So if you look at water actually has a crystal format, and it looks like this. It's a hexagon. But each one of those lines represents an H2O molecule. And when you combine those all together, you can put this is symmetrical, and will translate to numerous, it's not symmetrical because I'm drawing it, but it is actually symmetrical. You can see, you can draw these on top of each other for as long as you want, to your heart's content. Obviously, I'm not a great artist, but you can see how this can form a crystalline structure. If we go down a little bit, we're going to get 2 much more popular. So, I mean, if you want to take a second, you can guess which these 2 are. But this, and if you want to pause, you can. But this is NaCl, commonly known as table salt, and this is diamonds, the most popular crystal if you want to go there. But you can see this is their 3D structure. We just looked at the 2D structure. And these will then combine to make crystals. But these are the unit cells. And if you look at NaCl, you have a 2D unit cell that you can go off of too, where it looks something like that with Na and then Cl being on the outside. But I mean, this is the basis. Everything in the crystal is made off of this, and everything in that crystal is made off of this. And so you can kind of see how they're really intertwined here. And we're going to go in a little bit more depth right now on how they're applicable. Because we use something called a metrical matrix to truly find some things with crystals. So we can find angles of crystals, and we can find dimension. And we're going to be focusing on angles real quick, because I figured that was the one that would be a little bit easier to explain given the definition of the matrical matrix that I'm about to go over. But you can also use this for dimension. We're just not going to go over it right now. So the matricular matrix can be found using the dot product of the vectors v times w. And these are obviously, you get ax plus by plus c because it's three-dimensional here. And the same goes for w. But that equals vw cosine theta because we are using the dot product. Therefore, we can assume that cosine of theta equals v times the dot product of vw times v times w. Continuing, the length of v is equal to the dot product of v, that's w, which is then equal to v squared times the cosine of 0. But the cosine of 0 is just 1, so the length of v equals v squared. We can represent this as v transcribed d times the matricular matrix, which I'm going to give the formula below real quick, times the v that is not transcribed, so v of d. I get this is a lot confusing. I'm throwing out a lot of numbers here right now. This is important though. And if you look, g equals, just make sure I get this right, a squared, and people a lot smarter than me came up with this, and I'm not going to take credit for that at all. I am just trying to, that's a c by the way, c cosine. I'm just trying to showcase it, and I get that my y, the Greek letter is not as precise as it could be. I'm just trying to explain this though in a way that is more understandable, because when I first looked at all this, I was lost. Oh, b cosine a c squared. This makes sense because you're going to have an angle between c and b, you have an angle between b and a, and you're going to have an angle between a and c, right? And that's showcased in the formula. But we can then continue on with v transcribed, because we need to figure out what that is, right? This is equal to v1, v2, v3 in the matrix, and then v d is just equal to v1, v2, v3. So we're encompassing the entirety of the matrix. And then by taking the square root of v, of the dot product of v times v, so to the 1/2, we can get the formula we just talked about for the length of v squared, which equals v t d times g v d times, and then all that to the 1/2. And likewise, v times w would equal v t transcribed, g, and then w not transcribed, which will make more sense when we go into it in a second, but I'm just writing out all the formulas so when I go and use them later, we can really, you are familiar with them, at least to a certain extent, and obviously practice will make perfect in here. So going through everything, we have VW equals VW cosine theta, but we know that that equals V transcribed D times G V D to the 1/2, we just went over that, times the same thing with W, because W works the same way that G does. I'm going to run out of space here, and I understand that. W, D, and then that's to the 1/2. All that's times cosine theta. And all of that equals V, T, D, G, W, D, which we just went over. So, V transcribed T, D, G, W, D over the giant mess of formula we just wrote out. Sorry, I gotta make sure. I'm really wanting to make sure I do this right. So I'm taking my time, and I'm sorry if that's leading to a little bit of silence, but I think we can push through. D to the 1/2 equals cosine of theta. So that's how we're gonna use that formula to get cosine of theta in a second. So going into an example, let's say that we have a triclinic rhomboidite crystal that gives us numbers of A equals 10.497 angstrom, which is just A with a little circle on top. B equals 9.797 angstroms. C equals 12.185 angstrom. And I know that's not the actual symbol, but that's the symbol I'm using just so that you guys can see it more. I know it's a little bit more nuanced than that, but then we get the A angle equals 103 degrees. B angle equals 108.51 degrees. And the C angle equals 82.50 degrees. What's the material matrix? You can scroll back up, or you can rewind. We're going to use this, and we're going to put all the numbers in. I'm obviously going to just kind of put the numbers in. This is supposed to say BC cosine. I understand it's a little. Cosine of, just make sure I get it right, A. Cool. But if you paused and wanted to go through that, you'll get the numbers G equals 110.187009. Again, I'm just going through. I will say all these numbers will be rounded when we put it into a matrix. In my calculator, I tested it earlier, and it rounded some of the numbers. No worries. We're not really concerned. We're really trying to figure out how this all relates, because right now I've just given you a bunch of formulas and not too much to really go off of, but we're going to get there. Trust. And you see these numbers are the same because they're using the same values, just in different orders, which I thought was cool when I was first looking at this. Same with these two numbers. And 148.474225. Okay, cool. So what are we doing with that? That's just our regular matrix. Now first, we're going to get the angle between two zones in the crystal. So we're given the unit cell dimensions of two zones. We're trying to find the angle. We're trying to find the angle between the zones. So zone 1 is -1, 1, 2, and zone 2 is 2, 1, 3. And we can think of that as V and W. This is actually VTD, and this is WD, if you really want to think about it. So what we can do is now set up our formula from earlier, where we get R1 TD. We can use, actually it doesn't even have to be R1. It can be V. We can even use the same things that we did earlier. We don't have to because it's the same, but just for fun, we'll do that. I keep hitting R. W. D. And that's going to equal, I'm going to put it down here, -1, 1, 2, because the transcribed row is always going to be in that format. Our G value, which I will write out, even though I'm going to probably push it on space. I'm going to try to go smaller. Wait. Look at that. We can just move it over. Perfect. Now I'm going to have I'm going to actually have enough space for this. I'll even move this one over a little bit so that make sure the decimal point's really pronounced there. It's right and small, and I think I just kind of skipped over it, to be honest. And then you get negative 40.606321. And 148.474225. And then you're going to go 2, 1, 3, because that's the numbers. And then what we're going to do is we're going to use the dot product. So we're going to use this number times this number plus this number times this number plus this number times this number for that row, and that's going to give us a row number. And then we're going to do the same for the next row, and so on and so forth. So if you want to pause and do that, you can. I'm going to do that just a little quicker off screen so that the math is quicker and this video doesn't push the time limit I think it's going to be pushing. But what you should get, assuming you paused, is negative 1, 1, 2, because I haven't done anything with that yet, times 1, 1, 9, 7, 8, 2, 5, 0, 8. Again, if your calculator rounded, no problem. We should still get similar numbers here. And then we just do the exact same thing where it's bop plus bop, those numbers equals, and then that's going to equal 605. And then we're going to do the exact same process again, except we've got V, T, D, and you can check your work. That's the number you should get. So you get V of TD times G times V D, which then equals negative 1, 1, 2. And you're just trying to find all the values that you found earlier, but now you've been given, instead of having it as a formula, V of TD, instead of it being V1, V2, V3, is now 1, 2, or negative 1, 1, and 2. Kind of cool, at least to me it was negative 1, 1, 2. And then we're going to get the same numbers. I'm just going to put G this time because I don't want to write it all out again. And that number is literally the same. So if you want to go do the math again, you can just pause right here and write it down. For the sake of time, I'm just going to kind of use the same. And then this one's the column version. We'll do the same transcription process. And we will get this matrix this time. And I will write this one out just so that you guys can check your work if you are following along with me and doing the math, which you can, or you can just watch, and maybe I'll put a couple examples at the bottom that you can go through by yourself and check with a teacher or something of that nature. Oh, 943. And then we're going to do the same process where we do the dot product, and we're going to get 828.228581. Kind of interesting. How we're moving a ton of different pieces here that we've learned in math throughout the years, and putting it into basis and span and angles and just trying to figure out how crystals work. Anyways, next one we're going to do it for W. So W, because we need to figure out that for our equation to work. TD plus G, or times G. And the G works. It kind of looks weird, but we'll just roll with it. And this time it's 213 times G times 213. Again, not going to put G. I will for the next one, but you're going to do the same process, and I will scroll up for you guys if you want to see it in the original. That's a decimal point. Should have probably clarified that a little bit more. Anyways, continuing, that's going to equal 11.982 2508, 42.2660321, 337.356, 1748. Make sure you put the brackets. We're going to have 213. And we're going to do the same thing that we've done before. And we're going to get 12, 7, 8, 2, 9, 1, 0, 5, 8. So now we're going to go back to our original equation. We're going to get cosine of theta, so what we've been trying to find this entire time. And we've got v, because again, technically you could use any variable you want here. It's just I chose to use d because earlier we were using d, or v I mean, and that's what I wanted to use. Yeah, kind of nice. There's not strict variables you have to use, except for g, and the d, and the t. So maybe there are some strict variables, but that's not the point. And we're going back to our original equation. Which is why we did all this, to be fair. Oh, to the 1/2, remember, because you multiply them together, you'll get 1. Probably should have explained that a little bit better. I keep putting R2, because that's when the example I'm looking at from the University of, or is it SMU? I don't remember what that stands for. Does it that way. But I'm walking through it, because like I said, it is complicated on that thing. Let me tell you what. But we're going to plug in our numbers now. So 605, if we go all the way up, that's the first number we got, 605. And then 828, and then 112. So 605.0000131. So we got to start. Oh, I think I cut out. I think I forgot to put a 0 up here. I did. So if you were yelling at me because we're writing about to write a comment, I fixed it and I put one too many zeros down here. Probably wouldn't have done that. Luckily I did all this math beforehand, so this math has already been done beforehand. So it won't. To save time, obviously, I don't want to put you guys through terribly long videos, even though I know this one already is going to be extremely long. Then you get 0.5879884, which then you do the cosine of 0.58784, and you get theta equals 53.99 degrees. That's percentage degrees, which is the answer to the problem that we're going to beginning with. So that's useful because you don't want to, that's a really, I mean, it is kind of complex, but it's a way to get the angle between two separate points on a crystalline structure. And we can do the same thing using a matrix like we just did to find the dimension, to find the volume, but we're not going to do that today. I just wanted to give you guys a quick introduction into crystals and lattice structures and how you can use linear algebra to work with crystals, how crystals are conceptually very similar to linear algebra because you have vectors and spans. And instead of having a vector, you have a molecule that then gives you the kind of the code for the rest of the crystal. But hope you guys have a great day. Thank you guys for watching, and I will see you guys next time.